Hello again. This is Math 2233 coming to you from the College of DuPage. The title of this lecture is Normal Binomial Vectors, Oscillating Planes, and Oscillating Circles. Remember to be an active learner as you watch this video. The normal and binomial vectors. At a given point on a smooth curve R of t, there are many vectors that are orthogonal to the unit tangent vector capital T of t. We single out one by observing that because the magnitude of t, capital T of t, is 1, a constant for all t, capital T of t dotted with t prime of t is equal to 0. So t prime of t is orthogonal to t of t. Note that typically t prime at t itself is not a unit vector, but at any point where the curvature doesn't equal to 0, we can define the principal unit normal vector, capital N of t, or simply unit normal as capital N of t is equal to the vector t prime of t divided by the magnitude of t prime of t. We can think of the unit normal vector as indicating the direction in which the curve is turning at each point. The vector capital B of t equal capital T of t cross product with capital N of t is called the binormal vector because it's perpendicular to both t and n and is also a unit vector. And here's a picture showing what's happening. So B of t is perpendicular to those unit vectors. This is very important in differential geometry. And the tangent, normal, and binormal unit vectors, often called t, n, and b, or collectively the TNB frame, also called after a couple of people who did a lot of work in this area, together form an orthonormal basis spanning R3, and it's defined in the ways that we just did it. So you see at each point on the curve we have a three-dimensional vector that is very, very useful. So let's apply the formulas to solve this problem. Find the unit normal and binormal vectors for the circular helix, and here's the equation of the circular helix that we're doing. You know what to do. Let's see how you did. Well, we first are going to compute the ingredients needed for the unit normal vector. So we need to take the derivative of r of t, getting this. We need to know the magnitude of r prime at t, which is this. So then we can compute that t of t is this. You should make sure that you follow all these calculations. If we take the derivative of this, we get t prime of t is equal to this, and the magnitude of this is equal to 1 over the square root of 2. So n of t is equal to t prime of t over t of t, or the magnitude of t of t, and so we get this, and in pointy bracket terms this would be the normal vector. So that shows that the normal vector at any point on the helix is horizontal and points toward the z-axis. Now the binomial vector is capital T of t crossed with n of t. So I insert those unit vectors into my formula for cross product, and I get this as my answer. This is very similar to the kind of problem I could ask you. So when we can look at this at any point, and it is different at every point along the curve. And as I mentioned earlier, this plays an important role in differential geometry and in mechanical engineering applications associated with the motion of spacecraft. The plane determined by the normal and binormal vectors n and b at a point P on a curve is called the normal plane of the curve at P. It consists of all lines that are orthogonal to the tangent vector. The plane determined by the tangent vector and the normal vector is called the oscillating plane of C at P. The name comes from the Latin meaning kiss, and this is the plane that comes closest to containing the part of the curve near P. If we're dealing with a plane curve, the oscillating plane is simply the plane that contains the curve. The circle that lies in the oscillating plane of C at P has the same tangent as C at P and lies on the concave side of C, towards which the normal points, and has radius rho equal 1 over kappa. That's the reciprocal of the curvature, and this is called the oscillating circle, or the circle of curvature of C at P. You see, this gives you a nice geometric way to observe how fast the curvature is changing at a given point, or what is the curvature at a given point. It is a circle that best describes how C behaves at P. It shares the same tangent, normal, and curvature at P. So when would you use this? Well, any type of motion that can be modeled with a space curve has an associated TNB frame. This frame can be used to analyze the motion, including finding the rate of turning and twisting in the motion. And later on we'll talk about torsion as an additional component here. So, as examples then, race car drivers often navigate tracks that include banked turns. The TNB frame associated with the car's path around the track provides information about the twists and turns that the car's structure must endure during a race. Second example, while traveling in space, a shuttle must consistently monitor its motion in all directions. A pilot should be aware of the shuttle's TNB frame, which shows the direction of the motion and the turn. The frame also allows for calculation of curvature and torsion of the shuttle. Lastly, the pilot of a hang glider must consider the magnitude of turns and twisting motion. The TNB frame associated with the glider's flight allows these motions to be analyzed and graphed at any point in the flight. Let's apply our learnings then to find equations of the normal plane and oscillating plane of the helix that we talked about before. This is the helix we talked about before, and we're going to talk about this at the point 0, 1, and pi over 2. You know what to do. Let's see how you did. Okay, the point corresponding to t equal pi over 2, and the normal plane there has normal vector r prime at pi over 2. So when we took the derivative, getting r prime and substitute in, we get minus 1, 0, and 1. Make sure you validate these calculations. So the equation then is going to be, the equation of the plane is going to be this from our previous learnings. Or we can simplify this expression and get this. So z equals x plus pi over 2. The oscillating plane contains the vectors t and n, so its normal vector is t cross n is equal to b. And so we have, and we calculated this before, that b of t is equal to this, and when we put pi over 2 in, we get this. So the normal vector is 1 over square root of 2, 0, and 1 over square root of 2, but we could factor out the 1 over square root of 2 to get 1, 0, 1 as a simpler normal vector, and so the oscillating plane could be written this way, or solved this way. So you see we did this two different ways, and you can see that this is the plane that we get for this helix. Another example using these concepts. Find and graph the oscillating circle of the parabola y equals x squared at the origin. Recall we have studied this before, and beyond that, you know what to do. Let's see how you did. Okay, so previously we found that the curvature at 0 was 2. So the radius of the circle at the origin is 1 over kappa, or 1 over 2. And its center is going to be 0, 1/2, because we just go from the origin and we go the radius in one direction to get the center of the circle. So its equation is given by this: x squared, that's x minus 0 whole squared, this is y minus 1/2 whole squared, is equal to the radius squared, which is 1/4. And you can see that that in fact is what we get as the oscillating circle. And we could also use parametric equations for this, and these would be the parametric equations for that circle. X is equal to 1/2 cosine t, and y is equal to 1/2 plus 1/2 sine t. So we've actually talked about quite a few formulas here, so we summarized them. And again, this is for the TNB frame, and also reminding ourselves of curvature. So remember this for the unit tangent vector, this for the principal unit normal vector, this for the binormal vector, and this is several representations of the curvature. Again, you're going to be expected to know these and apply these on assessments. Now, here's a question about when would you use the oscillating circle. Well, recall that an oscillating circle is a curve that provides a visualization of the curvature at a particular point. So pilots of fighter jets must be sure to avoid exceeding certain limits of acceleration during turns. They will pass out if the pressure gets too great. The oscillating circle associates with the just space curve allows such acceleration values to be easily calculated. Train tracks must maintain a minimum radius of curvature to prevent the train from derailing during a turn. Engineers must always keep in mind the oscillating circle for the proposed track routes. And city planners try to minimize the space taken up by structures. Many parking garages use spirals to move up and down levels. To use minimal area, the spiral must contain a constant or nearly constant radius of curvature. The oscillating circle can be visualized by looking down the spiral from the top. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.